Okay, the second part of this section, we're going to look at the disk method. And what this does is it gives you a volume when you're revolving a particular function around an axis. So a lot of times when I think of this, I think of these Christmas bells that I've seen before. You've probably seen these before. You have some sort of a shape, and then you rotate that and unfold that, and you get this three-dimensional thing that looks like a Christmas or a wedding bell or something. Okay, so what I'm going to do first of all is show you kind of what's going on in this problem with this GeoGebra link. I'm going to click on the GeoGebra link, and then we'll go to the internet and take a look at this. So this is kind of a nice visualization that I found on the internet. So the idea is you've got some sort of a function. Now this one you have a polynomial function of degree 4. And we're going to revolve this around the x-axis. Now what we're going to be doing is we're going to go from x1 to x2. And I'm going to minimize the number of rectangles, kind of make that small. It's a little bit easier to see. And what I'm going to do is I'm going to revolve this around the x-axis. So you can watch this demonstration. And what it's doing is it's making a three-dimensional object. Kind of looks like a bottle. Kind of reminds me of the bottle on the old television show when I was a kid, I Dream of Jeannie, the Genie bottle. So it kind of reminds me of that. Of course, if we increase the number of rectangles on this, we're going to increase the accuracy of this. But the idea is we have circles. And when you're revolving something, you have a bunch of circles that are being made, and they are being summed from left to right. So that's a pretty nice demonstration of how revolution around the x-axis is going to look. Okay. Now if I go back here, here's another little demonstration that I found. I'm going to open up this website, and if you watch this thing, this is showing how you're revolving some sort of a function, and you're getting circles. Now all of these circles represent what we call disks, and we're getting some sort of a shape that to me looks a lot like a bell again. So you notice these cross sections are disks, and the disks have a certain width to it, but we can make that infinitesimally small. So that's what the idea is. Those are a couple of visuals that hopefully will help you a little bit to get a good understanding. Okay, now to begin with, we're going to look at this particular function here, and we're going to start with our first example, and I'll show you kind of the idea behind this then. Okay, so starting out on this, this is the definition of doing a disk method when you're revolving a function around the x-axis. So a couple of key things to make note of. You have to have a continuous function, and the function values need to be positive, and you're going to be continuous on this interval from a to b. And we're going to be bounded by the x-axis and then a couple of straight lines from a to b. So I'll explain what this formula is doing. So we're going to find the volume of this solid generated by revolving this. We're going to end up with pi f of x squared dx ab. Okay, now I'm going to back up one page here and kind of go through a couple of things on this to begin with before I do that example. So these are a couple of good visuals right here. So you've got this particular function. It's continuous from a to b, and the function values are positive. They're above the x-axis. So if you revolve this around the x-axis, you get some sort of a shape like this, which contains a bunch of circles. The cross sections are circles. This second diagram shows this pretty well. Notice that you have different circles, and the circle kind of starts big, and then you get a very small circle towards the end. So a couple of things to kind of develop our formula are going to be these two ideas. So first of all, the cross sections are circles, and that's what we're going to be focusing when we put together our integral. And the formula for an area of a circle is pi r squared. Okay, the radius, however, if you look at this diagram right here, the radius, and you'll kind of have a cross section kind of like this. I'm going to go up here and just kind of attempt to draw a circle as a cross section. And the idea on this is you'd have a radius, and that radius really would be the distance from that y value to the x-axis. So that right there would be your radius, and that radius is just going to be the function value, okay? So the radius is going to be given by whatever f of x is, okay? Just kind of look on that, and if I draw a second circle over here somewhere, well, the radius gets a little bit smaller, but the idea is it's just represented by that function value, okay? So that radius, I didn't draw that real accurate, but that radius is really just that function value, what that y value is right there. And then what you're going to do in this diagram is you would be integrating or summing up these disks from A to B, and then we'd be able to determine what our area function is. So the area function, we know that we have pi r squared for a circle. However, we're going to replace the radius with f of x, so we end up getting that the area is pi times f of x squared. So that would be the general formula that would be integrating then, okay? So that's what you have to understand as you're working with disks. And the other thing when we actually start doing our integral is these disks have a thickness of dx, okay? So we kind of have disks that are getting smaller and smaller and smaller, so that depth is going to be given by dx. Okay, so here's what you would be doing. You'd be doing, to find the volume, you'd be doing the integral from A to B of the area. And again, that represents the circle's area of the disk. Okay, and then this really represents the thickness. So and then again, we get pi f of x squared because f of x is the radius. So that's what you want to focus on is to understand the process. Okay, now I'll go to the next page, and what I'll do here is we'll begin to look at some examples that utilize this idea. So let's go to this example 4. I've drawn kind of a nice picture on this. Okay, so step 1, we do have a continuous function, and this problem says we're going to be bound by a curve. We have this function, which is a quadratic. And then we also have, we're bounded by the x-axis and the lines x equals 0 and x equals 2. So what this means is x equals 0, of course, is there. X equals 2 is there. So you're going to be integrating your disks, summing your disks from 0 to 2, okay? And if I was to go through and, again, just kind of sketch out a circular region right here. I'm going to put a little disk, try to get that fairly accurate there. What I would be doing there is I'm summing that disk. So what I need to do is I've got these kind of ideas. I've got a thickness of dx, and then the radius is really just going to be that function value. So that radius is just going to be whatever the function value is. It's going to change as you go left or right. Okay, so step 1 in setting this up is we need to find the area function, a of x. Okay, so we have the area of a circle is pi r squared. However, in our diagram, the radius is just the function value. So we're going to have f of x squared, and then we're going to replace that function with what it's equal to, x plus 1 to the second. So our area function is going to be pi times x plus 1 to the second, all raised to the second. Okay, like that. And then remember, you have a basic property of exponents that says if you have x to the m to the n, that's the basic property where you multiply your exponents. So what we're going to get for our area function then is we're going to have a of x is equal to pi times x plus 1 to the 4th power. So that's step 1, is figuring out the area function that you're going to be working with on the integral. Step 2 is we're going to set up the integral. So when we do the volume, we're going to integrate from the general formula a to b of a of x times d of x. Okay, like that. Okay, well in our function, we're going to be integrating from 0 to 2. So those will be the limits of our integration. Our area function is right here. That's going to be pi times x plus 1 to the fourth times dx. Okay, and then again, I want to stress on this right here is really just the area of a circle. Okay, that's the circle of your disk, so it's really pi r squared. And then this thing right here is the thickness of the disk. Okay, so that's what we're going to do. We got our integral set up. So now in step 3, we're going to do the integral and evaluate the integral. Then I'll show you how to check on your calculator. Okay, so what I'm going to do is I'm going to bring the constant of integration out. Pi is a constant, so that can come out in front of my integral. And then this is a good example of something you could do by u substitution. So what I'm going to do is I'm going to let u be that part. So at the side, I'm going to have u equals x plus 1. And see, that would allow us to have a u to the fourth integral. It's easy to integrate u to the fourth. And then du, we would want that to be the rest over the left of the integral dx, and it is. So in this case, du is going to be, the derivative of this is 1. So that's 1 times dx, or just dx. So we have that. Okay, so that part right there is going to get replaced with du. Now, since we're going to have a simple integral, I'm going to go ahead and I'm going to change these limits of integration. Okay, so when I do this, I'm going to have when x is equal to 0, u is going to be 0 plus 1, so u is 1. So that thing is going to change to 1. Okay, and then the second thing we're going to have is when x is equal to 2, the upper limit of integration, u is x plus 1, so that's going to be 2 plus 1, so that's going to be equal to 3. So that means that limit of integration is going to change to 3. So all I did was I just added 1 to get that set up then. Okay, so again, if you're changing the limit of integration, what you want to do is you want to use this. Okay, so that's what I did, is 0 plus 1 and 2 plus 1 to get those new limits of integration. Okay, so I'm going to go ahead and write the v integral, which is going to be pi times integral from 1 to 3 of u to the fourth times du. That'll be a very simple integral to do, so that's going to be pi. The antiderivative of u to the fourth is u to the fifth over 5, and we're going to evaluate that from 1 to 3. Okay, we don't worry about the constants, so we're going to have pi. By the fundamental theorem of calculus, I'm going to plug in the 3 to get 3 to the fifth over 5, plug in the 1 to get 1 to the fifth over 5, and then subtract the difference. So that's what I'll be working out. So that's going to be pi times 243 fifths minus 1 fifth. Okay, so that's going to be pi times 242 fifths. So that means the volume, the final answer, is going to be 242 pi. Hold on, I put the pi in the wrong place. So let's do it like this. Okay, so I'm going to have, for a final answer, 242 times pi all over 5. That will be my final solution to that problem then. Okay? Okay, now the other thing that I want to do on this pretty frequently as I'm teaching this is I want to pull up my graphing calculator to show you how you can check and verify. These are always really nice things to know how to do because you can make arithmetic mistakes pretty easily when you're doing the fundamental theorem of calculus. Let's go back to what we're integrating. So originally we were integrating pi times, and I'm going to put in x plus 1, and I'm going to raise that to the fourth power. So that's what we want to graph. We're going to integrate from 0 to 2. I'm checking this integral right here, basically. Okay, and on my window, I'm going to integrate from 0 to 2. So sometimes I like to do that kind of like that. Sometimes I like to expand my window a little bit further. So I'm going to go 0 to 2 by a scale of 1. Now, one thing I do on this is I look at my y values. So if I go second graph to look at the table, notice that when x is 2, that function value is 250. So since that's 250, what I'm going to do on this is I'm going to make my y's go from 0 to 300, maybe scaling that by 100. And then this should give us a really nice picture of our graph. So I'm going to graph this. So I'll have this function then, and then I'm going to go second, trace, to open up the calc menu. Then I'm going to go option 7, so I can just press 7. The lower limit is 0. The upper limit is 2. It should shade the region, and that'll give a decimal approximation. I just think that is just so incredibly cool. Okay, so what we end up having on this now is about 152.05. So I'm going to just sort of write this down. So the volume is about, in decimals, 152.05308. So if I was to take this answer, just clear this on a clear screen and just go 242 times pi over 5, and then I can do the drum roll and see if it's right. Okay, look at that, we're right. Okay, so that verifies that assuming that we set the integral up right, then the technology is going to tell us that we did the fundamental theorem correctly. Okay, all right, so that's a good starting example. I'll go now to the next page, and we'll work out a couple more examples. On example 5 on the next page, we've got a region that's triangular, and we're going to be revolving this around the x-axis again. So the idea, if I was to go through and just draw a disk, just to kind of help everybody get an idea of what's going on here, you would have a disk like that, and you'd have a bunch of disks. So you're going to have disks that you're integrating from 0 to 3. So we're going to work our integral out this way, just kind of integrating from there to there, summing up those disks. Okay. Now what happens on these disks here is if I go through and if I kind of show you a disk at the side like this, if you look at this cross section, that would be a disk. Okay, what we would have on this is that thickness is going to be represented by dx, and then you have a radius like that, so you'd have to figure out what that radius is, and that radius is the function value. So if you look at like this disk here, that radius is just the difference between those two y values. So that radius is just going to be the function value then. Okay, so step 1, what we're going to do is we're going to go ahead and build our area function, a of x. Okay, and what we know is we know the area of a circle is pi r squared. However, in our function, we know that the radius is just going to be the function f of x, and then we're going to square that. That's the general formula that you're given. So we have a of x equals pi. Now replace f of x with what it's equal to. The function is 2x. And that's already solved for y. So we'd have 2x to the second. Okay, if you clean this up a little bit, you would get pi times 4x to the second. So that area function that we're going to work with is 4 pi x to the second. Okay, so that's always the first step, is figure out that disk, that area of that disk. Okay, step 2, we're going to go ahead and set up our integral now. So our volume is going to be represented by the integral. We're going to go from 0 to 3. That's what the problem pretty clearly states, is we're integrating from 0 to 3. So we'll have those limits of integration. And we're going to be doing the function, okay, the area function. We're going to have 4 pi x squared times dx. And again, just want to keep stressing this, that right there is the area of the disk or the circle, and that right there is the thickness. So you're really, by doing this integral, you're working with a volume of a disk where the thickness is infinitesimally small, okay? So I'm going to go ahead just one more step and write this as 4 pi, taking out the constant, times integral from 0 to 3 of x squared dx. That's going to be a real simple integral to do then. Okay, step 3, we want to go ahead and do the integration. Okay. Okay, so when we do this, we're going to have the volume is going to be, we write down the constant. The antiderivative by power rule is going to be x to the third over 3. And we're going to be evaluating that from 0 to 3. Okay, I'm going to put that over 1, and I'm going to write this as 4 pi over 3. And then we're going to evaluate x to the third from 0 to 3. Okay, 4 pi over 3 is a constant, so that will multiply by our evaluation. So then we'd have the volume is 4 pi over 3. And by the fundamental theorem, we evaluate at 3, we'd have 3 to the third minus 0 to the third. So that will give 4 pi over 3 times 27 minus 0. So that's 4 pi over 3 times 27. Okay, you can reduce the fraction. 27 over 3 is 9. So it looks like the final result we're going to get is 9 times 4, or 36 pi. Okay, so that should be the final answer to the problem for our volume. Okay, again, I'll do kind of a quick check on the graphing calculator as I'm doing these problems. So when I pull this up, for my graphing calculator, we're going to do this integral. So we're going to do 4 pi. Okay, let's see. Let me do that one more time. We're going to do 4 pi times x squared. Okay, that's what we're going to graph. Now we're going to integrate from 0 to 3, so I'm going to go ahead and set up my window from 0 to 3. Okay, like that. You can look at the y values, so if you go second table, you're going to notice that when x is 3, that function has a pretty big y value. So I'm going to make the y's go maybe 0 to 150 by a scale, say, of 50. And that should be a pretty good representation of our graph. So we're graphing this function in order to check our integral. Okay, we're not graphing the y equals 2x. So again, I'm going to go second trace, option 7 to calculate the numeric integral. So we're going to have a lower limit of 0, upper limit of 3. It's going to shade. I just think that is so cool when I see that thing shading. That is just so awesome to me. So that gives an approximate answer of, you would end up, the volume would be approximately 113.09734. So if I went through now and took our answer, which is 36 pi, that should work out to be the same thing. Let's find out. Okay, and it does. It's the same thing. So technology verifies we have a correct answer on the problem. Okay? All right, nice example. Example 6, we have an exponential function this time. And again, we're going to be rotating this around the x-axis. It gives us y equals 0. Now, y equals 0 is just the x-axis. X equals 0 is just the y-axis. So we're bounded by those two lines. So the first thing I want to kind of look at here is in this problem, what are you bound by? So the idea is you're kind of bound by the x-axis. You're bound by the y and x-axis. You're also bound by the line ln4, and then you're bound by that curve. So you get that shaded region like that. Okay, so the idea is going to be, we're going to be integrating from left to right with our disks. So we're going to be going from 0 to ln4 on our integral. Okay, if you looked at cross sections again, if you want to continue to do that, you certainly can, just to kind of help you understand what's going on in the problem. So if I took like a disk, kind of like that, that's what we're working with, is that disk. So step 1 is we're going to look at working with finding that area function. That's how you want to start because you want to figure out what you're integrating. So again, the area of a circle is pi r squared. However, the radius is just the function value again. You're looking at a y value there, and you're looking at y equals 0. So that distance right there is the radius, so that will be the function value again. Okay, so what we'd have is we'd have the area would be pi r squared, but more specifically that would be f of x squared. And f of x is given as the function y equals e to the negative x. You have a exponential decay curve, so we would have a is equal to pi times e to the negative x squared. And I should be saying a of x on this really. So a of x is pi. Again, you multiply those exponents to get e to the negative 2x. Again, you're applying that rule, x to the m to the n equals x to the m times n. That's the basic thing we're doing. Okay, so that's step one. Step two, we're going to go ahead and we're going to build our integral, and then we'll do the integration. So our volume is going to be the integral. We're going to be integrating from left to right, x equals 0 to ln 4. So those will be our limits of integration. Okay, our function we're integrating is a of x. So that's pi e to the negative 2x times dx. That's the integral we're going to work. Again, I want to stress that this right here is giving the area of the disk. And then this thing right here is giving the thickness. So you're actually summing little disks, and the dx allows it to get infinitesimally small in thickness. Okay, step three, we're now going to go ahead and work out this integral then. So let me kind of do a little boundary here. So that's problem 2, or example 5. Okay, so we're going to go ahead and now do the integral. So we're going to take out the constant. We'll have pi times the integral from 0 ln 4 of e to the negative 2x times dx. Okay, one thing I want to mention on this too, you have a formula. If you're doing the integral of kx dx, that's equal to 1, I'll slide that over just a little bit, that's equal to 1 over k e to the kx plus c. So see, we can use that. You don't have to use u substitution, but you certainly could if you chose to. So it's up to you. You could let u be negative 2x, or you can just use this rule, which is what I'm going to do. So I'm going to have pi, the antiderivative of that thing right there is going to be 1 over the coefficient of x, like this formula says, times e to the negative 2x. And then we're going to integrate that from 0 to ln 4. All right, so putting that together, that gives negative pi over 2 when you multiply those two fractions together. And I'm going to go ahead and write this as 1 over e to the 2x. I think it's a little easier to evaluate. And then we're going to go 0 to ln 4. So we have our antiderivative. Now we're ready to evaluate this then. Okay, so let's go ahead and continue. So we'll have negative pi over 2 times 1 over e to the 2 ln 4 minus 1 over e to the 2 times 0, like that. And I'm going to write this as negative pi over 2. I'm going to write this as 1 over e to the ln 4 to the second minus 1 over e to the 0. Now there's a logarithm rule going on there too. So just one little thing I want to mention here is if you have couple of things. If you have a general logarithm, like if you have a times logarithm bx, you're allowed to bring that in front. So you're allowed to get log base bx to the a. That's why I did that. That's a fundamental rule of logarithms. Okay, now pushing on from here, we're going to have negative pi over 2. We're now going to have 1 over e to the ln 16, and then minus 1 over, and then e to the 0 is 1, so we get that. So now we're going to have negative pi over 2, and then this is going to be 1 over 16 minus 1 over 1. Okay, and again, the rule that I'm applying on this, you see this a lot in calculus also, is if you had say you have like p to the log base p of x, that's equal to x. And that's what I did there. See, if the base e matches the base of the logarithm, 16, that's the answer. That's a fundamental property of logarithms that we do pretty frequently in calculus. Okay, so now I'm going to have negative pi over 2. I'm going to get a common denominator. So I'm going to change 1 over 1 to 16 over 16. So that's going to be negative pi over 2 times negative 15/16. So it looks like that final answer is 15 pi over 32. Okay, so that should be the final solution to the problem. Okay, all right, let's pull up the calculator and let's do a quick checkaroo on this one. Okay, so let's check our integral. So what we're integrating is we're integrating pi e to the negative 2x. Let's graph that function, putting in the pi, and then e to the negative 2x, like that. So that's what we're going to be graphing. And we're going to go from 0 to ln 4. Okay. Now, one thing I want to show you on this now is if I do ln of 4, that's about 1.4 approximately. So we probably need to go 0 to 2. So on my window, I'm going to go like 0 to 2, like that. Now you can look at your y values. Again, if you go to your table, second graph, look at the table from 0 to 2. What did I just do? So at 2, see at 0, we're at pi, like that. So what I'm going to do is this. I don't know why it did that. There we go. That's better. Sometimes this thing just does the darndest things. Okay, so now what I'm going to do is, with my calculator, I'm going to go ahead. Let me get my calculator pulled up here. And I'm going to set up my window. So my window, I'm going to go 0 to 2. Then I'm going to go like, for y, I'm going to go like 0 to 4 by a scale of 1. Okay, and then that will give us a good graph, because again, what we're doing is we're checking this integral pi e to the negative 2x. So I want to make sure we got a good picture. That's exponential decay. We're going to integrate from 0 to ln 4. So I'm going to go second trace, option 7, lower limit is 0. Upper limit, just put in ln 4. It will shade it. It'll give us a decimal approximation now. So it's going to give that piece right there then. And then we can see if that's the... Okay, so I was just showing you on this with the calculator. And I went ahead and did 15 pi over 2 is 1.47. And the other thing I was going to do on this is, when I graphed this on the calculator and did the area, see that area turned out to be this right there, so that matches that. So they're both the same. You can see on your calculator that's the same. Okay, moving to the next page. Okay, going to do a couple of more illustrations here. Okay, now in example 7, I didn't give you a picture of the function. This is a pretty good example of one that you'd probably want to use technology on to draw a good picture of. So I'm going to pull up my graphing calculator, and we're going to go ahead and get a graph established on this and get everything cleared. So you want to put in the function, which is 1 over, then you want to do a square root, and under the square root 1 plus x to the second. And we're going to do that graph. Now, what we're doing is we're graphing from negative 1 to 1. So that's going to be pretty important that we set our window from 1 to 1 on x. And then for the y values, we're kind of looking at the positive x-axis, and we're going to do this. So on my window, I'm going to go negative 1 to 1. You can expand out from that a little bit if you want to, scale of 1. Okay, for y, I'm just going to look at my table of values again. So if I go second table, notice at negative 1, we're at 0.7, 0, we're at 1. So the biggest y value appears to be 1. So what I'm going to do is, you could go 0 to 1. I'm going to go like 0 to 2. And then that should give me a pretty good graph on here. So that's my window. So I'm going to go ahead and graph this. And we're going to be looking at this function. So I'm going to pull this over to the side and move this graph over here. Oh, that's not what I'm wanting to do. Okay, so I got my graph. I've got kind of a nice picture on here. So we're going to try to get our integral built on this then. Okay, so the way I had this set up is this was x is equal to -1 and x equals 1. That's how we're going to be integrating. And then we've got our curve. So our curve on this is y equals 1 over square root of 1 plus x squared. They also gave y equals 0, which is just the x-axis. So for boundaries on this problem, the boundaries we're going to have is we're going to be bound by x equals -1 and x equals 1. We're going to be bound by the x-axis and the curve. So the shaded region is going to be this curve right here. So that's what you're going to imagine being rotated around the x-axis to get what we call a solid of revolution. So that's what we're interested in doing, is this region right here. So again, what we're doing with this is just kind of think of your circular sections. So I'm going to just kind of put a circle there just for reference to kind of show you what we're doing. Okay, so that would be a circle. It would have thickness dx. Its radius would really be from the x-axis to some y value right there. So that would be the radius. So that radius would just be the whatever the function value is, like that. That radius is going to change as we go from left to right. Okay, so step one in this problem is we want to go ahead and we want to find that area function. This is always pretty much the same. So we know an area of a circle is pi r squared. We know in this diagram that the radius is just the function value. And then we know the function value on this is what I gave you right there. So I'm going to replace this and I'm going to get a of x is equal to pi, and then I'm going to square 1 over square root of 1 plus x squared. Okay, we're going to square the radical, it's going to go away, so we'll get a of x is equal to pi times 1 over 1 plus x squared. So I'll just rewrite that function as pi over 1 plus x squared. So that is actually a mathematical expression that's given the area of this circle. Okay, so step 2, we're going to set up the integral for the volume. So we're going to be integrating. Again, we're going to be integrating from left to right, summing up disks from left to right. So we're going to be moving from there to there. So that will give our limits of integration are going to be -1 to 1. And then we're going to be doing the area function, which is, I'm going to write this just as pi times 1 over 1 plus x squared times dx. Okay, and again, keep wanting to stress that that part right there is the area of the disk. And then this part right here is the thickness of that disk. So you're summing volumes of disks. Okay? All right, so when I set up this integral, I'm going to have v equals, and I'm going to bring the constant out to get pi times integral -1 to 1 of dx over 1 plus x squared. And then step 3, we're going to do the integral and evaluate using the fundamental theorem. Okay, a couple of things that are important in this problem. Number 1 is you have this basic integral rule. So we know that the integral of dx over 1 plus x squared is the inverse tangent of x plus c. Okay, so that's a fundamental rule that we're going to use on this then. Okay, so it's actually very easy to get this done. So that means you're going to have pi, the antiderivative of that is inverse tangent of x, and we're going to evaluate from -1 to 1. So that's going to give pi, we're going to have inverse tangent of 1 minus inverse tangent of -1, and we need to work that out. Now I'm going to pull up a unit circle for display. Okay, so like magic, I'm going to wave my magic wand and poof, up comes a unit circle. Now, you want to be able to create a unit circle. I'm doing this mainly for teaching purposes right here. There's a couple of key things that I want to remind you about when you're doing this. So first of all, the thing is, the inverse tangent's y over x. Okay, so what you would find on this, and hopefully your trig background is sufficient that you could pretty quickly see that at pi over 4, the tangent's 1 because y over x is going to be 1. Okay, so this is going to end up being the inverse tangent of 1 is pi over 4. Okay, now we need to find where the inverse tangent's -1. So that occurs here at that point right there. So see, if you look at this, you would end up having the inverse tangent's y over x. So you would have negative root 2 over 2 divided by root 2 over 2, which would be -1. But you can't say 7 pi over 4 because it's out of range. You have to say negative pi over 4. That's a real important thing to pay attention to when you're doing integrals with inverse trig functions. And the thing I want to remind you of is if you have y equals inverse tangent of x, one thing that you learned in a trig class, it's easy to forget, but the range of answers is from negative pi over 2 to pi over 2. So you cannot get an answer out of that range. So there's nothing going on there, nothing going on there. If you're in quadrant 1, you have to give an answer from 0 to pi over 2. If you're in quadrant 4, you have to give negative angles. So you have positive angles there and negative angles like that. That's something that you got to go back and remind yourself of. Okay. Now, if I work this out on here, I would have pi times pi over 4 plus pi over 4. Okay, so that's going to be pi times 2 pi over 4. And that's going to be 2 pi squared over 4. And then that reduces. So you would end up getting the volume is pi squared over 2 as your final answer to that problem. Or 1/2 pi squared should be what that volume is. So that is your answer. Okay. Okay, you got to pay attention to that unit circle on that one. That is a really big deal on that one. And make sure that you don't forget about those ranges of your inverse trig functions. Okay. Okay, to do a real quick check on the graphing calculator on this one. Okay, what we're integrating, we're going to go back and check this integral. So we're going to put in pi divided by, and then in parentheses, you got to have 1 plus x to the second. Okay, like that. So that's what we're integrating. And we're going to go from -1 to 1. I'm going to expand that a little bit and go -2 to 2. Because we do have, sometimes you have to expand that out a little further if you get an error. So I'm going to do that like that. If I go to my table of values, looks like I need to be up at least around 3.14. So I'm going to make my y go 0 to 4. And then I can graph that. So that should be a good window. Okay, that's the area we're going to do. Now we're going to go second trace, and we're going to integrate from -1 to 1. Okay, it will shade that region, and then we'll see if it's the same as this. So that's about 4, a decimal approximation is about 4.9348022. So now if I clear all this stuff and just take my answer, which is pi to the second divided by 2, let's see if we get the same thing. That we do. So it's verified and checked. So we've done our integration correct. Okay. Okay, so I'm going to do one last example to wrap us up, and this is going to be a revolving around the y-axis. So this one's going to kind of work like this. Same idea, except we're going to be revolving around y instead, like that. So we got example 8. All right, so the way this one is going to look is our disks are now going to go like this. So I'm going to try to draw a circle to kind of help you get a nice idea of how that goes. Okay, so we got that, and with this, so if I go through and look at my disk, okay, what's going to happen this time is the thickness of this disk this time is going to be dy. And then the radius is going to be going from, the y-axis over to some point on the curve. I didn't draw my circle real good, but that radius is going to be the distance between these two values right there. So that's going to be your radius, and it's a difference between x values. So step 1, what you have to do on this is the very first thing you have to do is take this function, which is a natural logarithm, and we're going to have to solve that for x. So we have y, come on, I got to draw this better. Okay, so we got y equals ln of x. Okay, that's really the same as y equals log base e of x. If you write that in exponential form, you say e to the y is equal to x. So instead of looking at that function that way, I'm going to look at that function as x equals e to the y. Okay, because that's what I got to do. First of all, now I'm going to be doing my integration from 0 to 2. So this time I'm integrating in the y direction from bottom to top. So I'm going from 0 to 2. So I'm going to do my integral from 0 to 2. The disks are being added from 0 to 2, going in the y direction. Okay, so what we would do then in step 2 is we'd set up our area function. This time it's area with respect to y. So it's pi r squared. However, that's going to be pi times f of y squared this time. And f of y, remember we had to solve this for x, is e to the y. We got to have our variables expressed in terms of y. So we're going to have pi times e to the y to the second power, or that's pi e to the 2y, is going to be our area function. Okay, so we got that set up. Step 3, we're going to set our integral up, okay, which should be pretty simple. So we're going to have, for our volume, we're going to integrate this time from 0 to 2. Okay, like we're integrating in the y direction. And our function we're integrating is pi e to the 2y times dy. Okay, now again, this is the area of the disk. And then this is the thickness of the disk. So now we're ready to go through and integrate this and get an answer. Okay, so this should be a fairly simple integral. So we're going to pull out the pi. So we have pi integral 0 to 2 of e to the 2y times dy. Okay, that's going to be pi. And again, if you do an integral of kx or ky, you're going to say 1 over 2 e to the 2y. That's our antiderivative, and you're going to evaluate that from 0 to 2. So that's going to give pi over 2, and then we're going to integrate e to the 2y from 0 to 2. So that will end up giving pi over 2 times e to the 2 times 2 minus e to the 2 times 0. So that will give an answer of pi over 2 times e to the 4th minus e to the 0. So the final answer should be pi over 2 times e to the 4th minus 1. That's your final solution on that problem. So the only difference is you are integrating in the y direction. Okay, so that is your answer to your problem, like that. Okay, so that will wrap up this part, the disk method. That gives you lots of good illustrations of how the disk method works. It's pretty simple. Integral shouldn't be too bad. So hopefully that will help you to understand everything on that. Okay, have a good day.